no idea perhaps in terms of audience. And so I think I have changed the slides a bit on the train, but we'll see how it flies.
Okay, so Tamas is another contributor to this book project I mentioned before, and Tamas is a researcher at Johns Hopkins. And I'm really appreciative that he made it because Tamas flew from Holland yesterday, spent the whole 10 hours with his family last night, and took the first train up here this morning. So he gets
I'm going back.
Most hardcore travel schedule. So tell us about photometric redshift in Bayesian inference.
Well, it's a topic that's sort of close to my heart because back in the old days I worked on this, and then I abandoned it completely. I sort of came back recently again because of the pressure that these new surveys are sort of. As a steep hand start, all these photometric surveys that are coming online. So anyway, before I start, because not everybody's an astronomer, maybe I should just say that we live in a strange universe that's 70% dark energy. We don't know what it is. 26% of dark matter, and 4% of ordinary matter, like normal matter. And that's what we look at, right? It's a luminous matter. So we have to do that. And in fact, what astronomers do is they beam photons, nothing else. Right? They can beam the photons different ways. They can beam them in space, good images. You can beam them in time. You can beam them in wavelength. So that's pretty much it. That's what the photon has, not a lot of the properties. So depending on how we beam them in these parameters, we get images and so on, for pictures and spectra. So especially in wavelengths, I think it's important to distinguish between the narrow beams, where we get these spectra with narrow line features that we can compare against the lab and measure various physical properties from them. And the broadband colors that you get from single filters. So it really is as if you were taking your camera, putting a red filter in front, taking a picture, green filter, picture, and so on. Just like your camera, in fact, it has on the CCDs. So anyway, and then you have really wide, broad bands that you can make these colors. The point to make is, of course, this is expensive. It's really hard to do. It takes a long time. And this is much easier, taking pictures. We are really good at. So just to give you a comparison, the Sloan, which is this big digital sky survey we are so proud of, spent most of its time in spectroscopy. And it could observe about 1 million galaxies or so, altogether 1.5 million sources, down to a fairly, by today's standards, fairly bright limit, 17.7 magnitudes. And in the photometric, on the other hand, it's producing just hundreds of millions, 400 million sources down to really faint magnitudes. So there's really lots of information in there that you would want to get at. And it's pretty pictures, of course, for those of you who are not astronomers, colors, shapes, all sorts of things that you can see or not see in this picture. I mean, the Sloan database has 400 parameters measured for every one of these things. Right? So we have lots of data that we can mine, and there's a lot of information in there. So we want to get sophisticated about how we actually extract that information and how we go about constraining the physical properties of these sources based on the measurements that we can extract from these pictures. So, and there are various attempts at that. Let's see. And of course, in this quest, models are useful, various models, statistical and theoretical. It's not always appreciated. People have been really very pragmatic for a long time. Okay, what are the multicolor challenges? First, identification of sources, merging the different wavelengths measurements into a multicolor catalog is a big challenge. I won't talk about that, although that's an interesting problem itself. Essentially looking for things that should be there, but we don't see them. They are in certain wavelengths missing. Those are also interesting things, and you need a different approach to essentially find those, knowing the geometry of the observations, effectively. What I would like to talk about today is just simply how we try to go about interpret the data and get information or constraints on the physics from these measurements. Photometric redshifts, that's sort of the label on this whole topic. And it's been around for a long, long time. I won't talk about these, just to show you that in 1962, the first paper was written about this topic. It's an old topic, 50 years or so, and it's been extremely pragmatic. This is the kind of problem that everybody says, probably here, oh, I can do it in 5 minutes. Right? I said the same thing 10 years ago when I looked at it. Because it's a regression problem, if you like. It's you have a sort of magnitude, say 5 numbers, and you want to predict another number, which is the redshift, the distance of the galaxy. It's a very simple thing, 5 parameters in, 1 parameter out. Why is it hard? And of course, people tried everything that you can imagine. Early proof of concepts were just fitting polynomials, piecewise linear fits. More recently, random forest and neural nets and support vector machines and Gaussian point processes. And conceptually, they are very similar. And they can do a lot of things, but not everything. Especially when you are getting away from your training set and you're in trouble because you're not sampling the space anymore, so you don't know what the universe is like there. So another class of techniques tries to deal with that, which is you try to figure out or model high-resolution spectra of these objects, and then feed them through your telescope virtually, and compare those colors to the observations. And by comparing them, you can look for the right, best fitting redshift, for example. Like this would be, say, 4 measurements of the broadband colors, and then you would want to pick the right template that goes from red to blue. And of course, you also have a shift in there. So it's fairly complicated, although I take it back. It's very simple. Okay. The most sophistication I guess we got to was 10 years ago is when we tried to do some sort of linear modeling, so have eigenspectra, and instead of just having a bunch of discrete sort of spectra, just have linear combinations that span the larger spectrum space. In this case, this galaxy is being projected onto this, and then see the reconstruction and residual. So it's fairly well and representing the galaxies, but the problem is that, of course, in that high-dimensional space, even if it's just 3 dimensions, galaxies occupy a lower dimensional manifold, and you have practically a sausage, right? So all these things out there are non-physical. You try to constrain them onto this sausage, and if you do, then you get much better constraints on the redshift. So this is sort of the embedding that we already saw 10 years ago, that there is this low-dimensional thing for the galaxies. Maybe not 3 dimensions, but not too many. So you can only do this photometric redshift business because of this, because the galaxies are not infinite dimensional. Okay, so that's an interesting piece of hint there. And then, of course, if you have some type parameter, then you can get self-consistent estimates for redshift sometimes. Okay. So just to summarize the traditional methods, you can do either empirics, and then you do really quick fitting functions and just evaluate them, but then you can't extrapolate, or you can do the template fitting. And of course, here the problem is that the templates are what they are. They either perform or they don't. So we try to do something really naive early on to learn these templates from the photometry, and this was part of what I worked on that 10 years ago, is that because you see these galaxies at different redshifts, different distances, you actually observe with these broadbands different parts of its spectra. So they actually overlap. So every line here is an object, essentially, and these are supposed to show you the coverage of the observables. So even though we have 5 numbers for each galaxy, because they have a lower dimensional manifold underneath, you can actually reconstruct, or hope to reconstruct these templates to some limit. And sure enough, some very simple technique where you look for the best fitting spectrum for each object, and then you try to correct it to match the photometry slightly better, and then do this over the whole ensemble helps. And you can essentially, as a side product, improve the redshift estimation. Okay, so you go from here to here. Okay, so this is not what I want to talk about. This is sort of just the warm-up for the whole problem. So now you are photology experts by today's standards. So you know everything about photometric redshifts. The question is, how do we make sense of all this? How do we put all these methods into context and try to figure out what to do next? Because it seems to many today that we have exhausted all the possibilities. We have tried all the machine learning techniques, and we get to the same results with every one of them at this point. But is that a limit, or is it just that we are missing something? Okay. So we talked about the redshift estimation, but in fact we should be considering this as a more general inversion problem. And this might be something, a more general discussion at this point that you might be more interested in. So if you have, say, 5 numbers that comes in, and you want to get out a bunch of things, not just one redshift, but its luminosity, its type, its red, and so on, then how do we go about this inversion? So maybe many of you have been working on this type of problems already, and you will hopefully have some input for me in the talk. And of course, you would want not just the estimate of these parameters, but you would want the full product density function. You would want to get the full PDF mapped out for you, so that you can actually do proper base analysis on this. All right, how do we do this? Start from scratch. We have a training set that has some photometric observables, X. So this is, say, the colors in some, so say red, green, and blue. We have some colors here. And then we measure some parameters for that. This is given. We know this training set. Then comes a query point, or a whole query set, with different measurements, but they are still broadband colors. So maybe it's not red, green, and blue, but maybe it's somewhat purple in the middle, but not too off, hopefully. Could be ultraviolet. And then the question is, how do we go about and estimate the density function of the physics given a query point? For this, we can use a model that connects the observables X and Y. So you can think of, for example, in the previous case, some templates that would give you the coverage over the spectral, the wavelengths range, and then you could marginalize over to get this dependence. So this is something that we actually have. You could make up these models. So if you have this model that can connect these two observables, and you have a prior on that, then how do we get to this? And as soon as we ask the question in this setting, I think it's sort of much easier to come up with the answer. Next slide, I will show you the answer. So essentially, you need 2 components to it. You have to be able to go from the observed query point to the observable space of the training set, which is the first step, and it's just a couple of integrals over the function that we looked at before. So this is a very simple thing. You transform your query point observation into a observation in the other space through the model. And this is something people actually do. People would come up with empirical formulas. They would fit the magnitudes with little color terms and differences and so on, linear approximations. So people do this, but here we actually use a model, a proper model, and propagate the uncertainties as well at the same time. So this is a full product density function on X. Okay, the second component we need is the relation between X and psi, so the physics and the observables in X space. And this is something what the empirical methods do. They would take a fitting function, just like this, and that's a relation. It's a very special relation because we know that there are degeneracies. So it really is a wrong assumption to some extent, or there are places in the parameter space that have degeneracies, and in those, this is not a good approximation. So instead, what we should be taking is a conditional probability. So for a given X, what sort of physics there could be. And because there's not everything is captured in the observations, there's always going to be a spreading here. Okay. And of course, this is just a special kind of relation if you have the usual restriction. But in fact, you could measure this general relation on the training set. Now, how you do it, that's a hard problem. But conceptually it's simple. All you have to do is measure the joint probability and divide by the marginal. Or somehow go about estimating the conditional density directly. But this is essentially one key element that we would have to do. And I'm hoping somebody would have a good answer to this. I'll show you what I did so far. But anyway. And then, of course, the integral of these two dot product will give you the final result, and then you're done, you're golden. If you really want to get the estimate, then you can just essentially integrate over this and get the expectation value of the value. Okay. If you want to get the properties of the samples, you can just average over these things, the PDFs. This is something that people always struggle with when they have estimates, because then you have to deconvolve the errors that you make. So if you have a if you want, say, a shell of sources out there, sort of at given distance, you want to set minimum and maximum distances on these samples, then you can only do this in this estimated parameter space. If you do it, then of course you won't get that sharp boundary. The errors will actually smooth it out, and that's something you have to deconvolve. Not really simple. In this case, it's something easy to do. Okay, selection effects. Again, something that we always discard when we do PhotoZs, or we used to do PhotoZs, is that you don't actually know whether the training set is giving you any constraints on the given new source that you're looking at or not. But you could define a window function in terms of the observable quantities. Say this survey is brighter than 17.7 magnitudes. And that defines a window function that you could, in the X space, that you could just integrate with this probability density function and get a number that will tell you how far you are from the training set. So this is something that's really useful to have in principle. Also, because of the selection function, you can't measure the relation, the true relation on the training set. You can only measure it on the training set. So the underlying relation would be, of course, a simple Bayes rule away from you. And what sits on the other side here as a multiplier is the selection function, where here you have the selection function as a function of both the observable and the physics. And here you only have just the observable. So if you're smart enough to select your training set just based on the quantities that you want to use in the estimation, then you're fine. Then you can actually, these things cancel out, and you actually really measure it, and you can recover the true relation. These are kind of things that we never thought of before, but it seems like seems obvious in this setting. Okay. Of course, there are still problems because getting physical properties is a hard problem, and sometimes you systematically miss certain things. So life is not exactly as simple as I picture it. Okay, so now with this framework in hand, we can go back and look at the previous methods that people used, and look at, say, template fitting. How does this fit in this picture? You would say, but there is no training set, so how do we talk about template fitting in this setting? Well, you can create one. So if you have templates, you have spectra that have types and redshifts, then you can just generate for a grid of parameters these training points. And then if you put in essentially 0 error on their accuracy, you claim that their photometry is perfect, then you can do the whole integrals, and what you end up with is what people use, essentially MLE type of things. You get the distribution as essentially a grid in redshift space or this physical space. And for every bit point, you have a weight that's given by the likelihood and the prior if you had one. Most people would just essentially ignore this and try to get the smooth estimate just average over. And that's what people use for template fitting. When they include a prior, they call it Bayesian for network shifts. Okay, so that's template fitting. Now for empirical estimates, it's interesting. So again, you can say, what if I just say that my relation, the photometry and the redshift, is given by delta, where the measured training point, the redshift is sitting in there. Then if I go with this and estimate and calculate the average, the expected redshift for this distribution, so here I have the result of the whole unified discussion of formalism, and this is just the redshift integrated over. Then of course, flipping the integrals and diseating the integral over redshift, you end up with a integral on x that we can just sort of approximate, if you like, with the sum that we have the training points redshifts. We have a similarity that's defined by this model between x and y, and there is a delta x term there, the volume. And in fact, this is what people use all the time. They would use averaged redshifts in various methods. So a locally linear fit would do this. Random forest would do this. There are actually explicit weighting redshift methods that do exactly like this. The only thing that they don't do is they don't include this volume element, which makes all these techniques sensitive to the training set. If it's not representative, then they won't work. So the density estimation again shows up even in here. People don't account for it usually, unfortunately. Of course, you can go about coming up with physically motivated models or similarities. The simplest you can do is essentially saying that if x and y are the same parameter space, say both RGB, that's right, RGB colors, say, then you could say, oh, I just parameterize the same space and have a flat prior on it, and you get essentially the similarity, which is the convolution of the two errors. Okay. So what I did was to just have a look at this and see how sane or insane this would be. I did a kernel density estimation to get the empirical relation out of this. And this is looking at Sloan data, so the sketch that I mentioned briefly before is a really valuable data set in many ways. It has lots of redshifts that you can play with and test these scenarios. And what this figure shows is what I get out of it. So the kernel density estimation, and maybe these are the pretty pictures that I picked, because this is a presentation anyway, but those will give you fairly good estimates, but they are bumpy. They are going to be somewhat noisy, and that's that. And then when you smooth it with the photometric errors, this is where the query points photometric value comes in. Then it becomes smoother, but yet not that much wider. And you can do the same thing for red galaxies, use different redshifts. So you can see how bumpy the blue curve is, but then it gets to red bridged over for a given query point, and here too. And then the green is actually showing you the true redshift. So in this case, it is worked very well. Blue galaxies are harder to do. They have a more exponential spectrum that is just hard to do. And of course, at high redshifts, they get really noisy, and they get also very, not very well sampled, so that just completely falls apart. But it's good to see that it actually happens. I brushed over one thing I wanted to mention here, and that was, well, okay, maybe here I can briefly mention this. This is practically kernel density estimation. Sorry, take it back. Kernel regression, except it's a generalization in a way. Oh, I did have it here, but I just didn't say it. Where you actually fold in the uncertainties as well. So it's essentially kernel regression, but with the uncertainties of the points. But again, very often we don't see in these derivations, and this is what astronomers always need. So, okay, how do we go? Well, we understand how this explains sort of how the previous methods work, but what's the next step? How can we improve? And one obvious thing is that you can now do empirical type of fittings or empirical type of relation mapping that we know works very well, but without the limitation of getting the same parameter space. Because if you have a model, you can actually go through this model transformation and use any training set, even if it's different colors. What you need, especially if you are considering very different observations, is a good prior. And in fact, all the physics is in the prior. So one approach could be that we don't bother with really complicated physical models of the spectra, but instead we take some generic complete basis over the wavelength range that we have, whichever quantization it gives you, and then solve for the prior, because that's what have all the spectra in it. And the way you could solve for it is, of course, the consistence that the density of the points in your query set, for example, will have to match, for a good model, will have to match the density of the model. So if you had, this is just a function that tells you for a given, for a given parameter what sort of photometry you would get. And this is the prior that we don't know. But again, on the other side is the density that we can compare to the measured ones. So this we have, this we know. And then potentially we could solve for with some smart deconvolution techniques for this prior. And then that would be a really big improvement. Yet again, it's hard because we can't simply parameterize it, so we need some sort of non-parametric approach here to do this deconvolution. And this is kind of where I'm stuck with that kind of stuff. So okay, plus good things first. So the Bayesian approach puts all these things on a firm ground. I was going really fast, maybe too fast. I was trying to go fast because I'm hoping that you will actually give me feedback. If I didn't say it out loud enough in the beginning, then I'm saying it now. I'm really hoping that the problems that I will soon tell you are problems that you have encountered and maybe you have solutions for, or just tell me they lost. But anyway, the plus things first. So this proper statistical inference seems to be giving us a really good framework for this problem, because it's telling us how all previous techniques were related, how they, why and how they are good, and also telling us where they are not good and why they are not good. That's a good thing. And they also give you the opportunity to put all the other things that you like in terms of physics. The problem is that, maybe I have a slide about that. Of course, well, I mean, it becomes hard at some point. You will have to do some computing, and there are things to be done, but no, I don't have another slide. I thought I had another slide on the problems. So the problems are manifold. One is, and that's for astronomers, understanding uncertainties of the observations. That's ultimately what drives your constraints. The smaller the errors, the better you can constrain the physics. We can leave that up to astronomers. But then we need tools that will give us the conditional densities. It's a very generic problem, it seems, that you could just create a conditional density for anything on a training set. It's kind of like regression, except it's a more general problem. Regression would be a special case of this. So I don't know if I'm being too demanding or it's too optimistic to have such a tool, but perhaps you have an idea. And the other one is, I think the prior that I mentioned before, which is how do I do these kind of non-parametric Bayesian evolutions, if it's doable at all. With that, I stop here, and thank you for your attention, and please help me.
Any questions or suggestions for Tamas? Yes.
so this posterior I was going for is per object, right?
Yes.
So this would be a posterior probability density function on the physics given a observation. And yes, it's true that we have a whole ensemble of them that we can use to learn about the manifold. It's what we have in a manifold. But we don't actually understand what can model just yet very well. But with the streaming, I can see how you could use a streaming algorithm to learn about the manifold itself. Is such shape, perhaps.
Well, I just floated it out to see if it helped the computation. It doesn't sound like it does.
For see that one, I see that we did with this. Other than you can do the streaming way. So yes, for that we could use this. I did think about that before. Conditional densities, anyone? No.
Just a comment, but it's probably more discouraging. Convolution. And so in statistics, it's called density deconvolution or decomposition. There's a lot known about it, and it's a very discouraging story. In even one dimension, if you try to do straightforward density deconvolution, so imagine kernel density estimate that you're going to do deconvolve it for you. If your uncertainties are Gaussian, not only is it, typically with non-parametric things, your capacity time convergence rates are slower than your net, right? They're like maybe 2 1/3 or something like that. For density deconvolution, it's logarithmic, which is basically saying it's not possible. But the way they've been making progress is to give up trying to be non-parametric, so doing something semi-parametric. It's basically, even in one dimension, you have to introduce some kind of structure into the problem, which inevitably introduces some bias if you don't really know what nature is doing. But they find that provided you're willing to live with a little bit of bias, you greatly reduce variance and get better behavior from it by not trying to.
We spent the last 50 years doing those kind of things in a very exploratory and ad hoc fashion. And I'm hoping that from stating the problem in this setting, where we actually see the problems explicitly, then maybe we can actually zoom in on them easier. But if you tell me that it's impossible to do it, then maybe it's just that's why we haven't done it in 50 years.
Also, one of the things that I've never been satisfied with in my own I'm not a statistician, so is that this density deconvolution aspect is something that is pretty much new with you introducing. The previous methods didn't really try to handle this uncertainty. So my impression, kind of my intuition of what happens is that you must converge fairly quickly first, and this logarithmic behavior must happen later when you're trying to learn the details of the distribution. And so, what's kind of interesting to me here is that we have had some success in the past, and is it that we're now reaching this regime where trying to do things really non-parametrically is just coming up against this logarithmic wall, or is it just that we don't know clever enough about models or
I mean, that is the thing, right? That the whole field evolved because of their success. Yes, but there hasn't been any systematic approach to it, so sort of it were just proofs of concepts here and there. You could show that it works in this case, it works in this case, and it doesn't work in this case so well, but careful, maybe it will work later. Any more advice, suggestion?
There's someone in UK. He works with climate models and he tries to condition this Bayesian inference, condition the type of the physics in the climate model from ensembles of many, multimodal ensembles. And he tries something like where he inputs the ensemble and then he somehow chooses the model in the way you have it, conditioning, having the prior on the model. I don't know the details. I just remember seeing him. His name is Jonathan Rouget. He's in Bristol now. He was before in Durham, working with Goldstein.
Look up.
Yeah.
What about Chris Miller's, like his C4 stuff? So he uses density and photometric redshift. He just uses photometric redshifts and colors of galaxies.
That's clusters.
Yeah, but he's using the colors and to get the distances and to look for clustering in the color space and in the redshift space. So he's leveraging both sides in a way. I don't know if you know about that paper.
So you're saying that you could actually fold in the clustering information into the same thing?
Maybe so.
Well, yes. So that's something I've been exploring in two different ways, and I didn't think of talking about it today. But it seems to me that although it should give you constraints, yet again more observables you would want to you would have to model, you'd have to put in. So yes, ideally you would like to solve for the clustering of the galaxies and their distance at the same time.
That's what we're looking. That's the.
But it just made the problem even harder. But yes, I did try two approaches, and I don't know if in PDF I definitely doesn't have them. But yeah, so one approach has been essentially to have a big GPU code solving for all the redshifts. Essentially have the photo Z as a prior, essentially what sort of redshift I can imagine for that object, and trying to do this humongous optimization for the galaxies so that they would actually match the correlation function. So I know what the correlation function of the galaxy should be. I was doing the 2D correlation, sigma pi correlation function. That worked actually surprisingly well. What you get is that the density, the distribution of the redshift. So if I say plot here Z spec minus Z photo Z, so the estimate versus the truth delta, then this is what the photo Z would give you. Now if I start to solve for the clustering at the same time, then about 50 megaparsec or so, I can actually vacate the histogram and put them all into a table, something like that. So to some extent it works, but of course beyond certain imagination. And again, this is a humongous parameter space to optimize, even though it might be. So you never know if you get to the right point, but it's just a blind thing, just some maximum likelihood type of thing. Optimizing the actually works surprisingly well for this ideal test case. It was real galaxies, real spectra, Sloan, but I took half the galaxies practically with real redshifts, so I actually had something for clustering to start with, but I can crystallize on the rest of the galaxies.
Okay, well, if you have any other crazy ideas, talk to Tamas afterwards, please. Okay, thank you, Tamas, again.